Let's now work through an example using our newly introduced notation for definite integrals. Here's a summary of what we've talked about so far. If a function f is integrable on an interval a to b, then this quantity here on the left-hand side, which is the definite integral of f from x equals a to x equals b, is defined to be the limiting value of these Riemann sum, where this delta x represents the width of our approximating rectangle and is given by this quantity here, b minus a over n. And in this case, x sub I is the right-hand endpoint of each interval, which we're using as the sample point in this case. Let's now work through example 5.2.1 from the textbook. The example asks us to express this limiting Riemann sum given here as a definite integral on the interval from x equals 0 to x equals pi. And in order to do this, we simply need to look at Theorem 4 and understand how the notation of definite integrals matches up to the notation of the limit of a Riemann sum. The first thing we can see is that the function f of x in this case is given by f of x equals x cubed plus x times sine x. The second thing we can recognize is that the lower limit of integration, a, is 0 here because we're integrating over the interval from 0 to pi, and the upper limit of integration is pi, again because we're integrating over the interval from 0 to pi. So we have f of x equals x cubed plus x times sine x, and we have the lower and upper limits of integration as being 0 and pi respectively. With this notation in hand, we can now write this limit of the Riemann sum as follows. The limit as n goes to infinity of this Riemann sum is equal to this definite integral here. It's the integral of x cubed plus x times sine x. This is our quantity f of x from Theorem 4. And this integral is taken from x equals 0 to x equals pi. So the lower limit of integration is 0 and the upper limit of integration is pi here. And we use dx to indicate that our variable of integration is x.